second postdoc at the University of Virginia, and he then got a position in Paris at the IAP. He didn't stay there very long, and then got another position at Columbia University, where he has been spending the last 4 years. So Kristen works on several topics, including accretion flow theory, compact objects, the formation of exoplanets, and so on. And today he's going to tell us more about the atmospheres of exoplanets.
Thank you, Brice. I actually don't work so much on compact objects anymore. I'm busy with planets. They're not so compact. No. So this morning I went to get a coffee. I'm staying at Massey College, and then at the end of the street there is this old building, and I don't know how many of it's just a university admission office. I don't know how many of you know, but there is a plate there that says it used to be the headquarters of Meteorological Services of Canada, and they would do predictions. So I thought that was pretty funny. I was thinking about my talk, and specifically, I imagine people working there, 100 years ago. This is a really old institute. Would think it would be really crazy to think that you might try to understand what's going on in the atmospheres of distant worlds. But so my goal with the talk is basically to tell you that I think we have a shot at this. I don't know how good a shot, and we don't know yet, but we have a shot at really trying to understand what's going on in these atmospheres, not in the sense of making predictions, but at least understanding qualitatively the behavior, the response of these atmospheres to very unusual forcing conditions that are not found in the solar system. And even from that, we might learn actually about what's going on in the solar system. So that's basically the broad context of the talk. My main collaborators are 2 graduate students, Emilia Raucher, Dave Spiegel, and James Cho, who have been working on this for a few years now at the University of London. The talk will focus to a large extent on hot Jupiters. So we know about nearly 300 extrasolar planets. I haven't checked the count this morning. And there is a very interesting subclass of extrasolar planets, these hot Jupiters, which are found like within, let's say, 0.1 AU of their sun-like star. And they're so close to, well, they're interesting for a variety of reasons, but one of them is that observationally, some of them are found to transit, and that gives us great information about what's going on with these planets. And from the point of view of the talk, what is very interesting and was pointed out, I guess, a few years ago in some of these papers, is that these giant planets are found in conditions of forcing that are very unusual, not found in the solar system. The idea is that the tides from the star is so strong that we believe the planet has had time to synchronize its spin with its orbit, and so basically we're dealing with a big ball of gaseous giant planets frying under the radiation from its star with a permanent day side and permanent night side. And obviously the gas is not going to be happy to stay there with hot, well, maybe it's not so obvious actually, but we know the gas will want to try to redistribute the heat from the day side to the night side, and this is, in a nutshell, the problem that is posed to us from a theoretical point of view. Can we understand what's going on in this atmosphere of these planets? How well will the heat be redistributed, and in what way will it be redistributed from the day side to the night side? And again, this is something that we don't have in the solar system. There might be arguments that could be made that Venus has some analogy, actually, and that's an interesting analogy to develop, I think. But the basic point here is that if we're able to get data on these planets, and I'll discuss the data in a moment, and understand what's going on, these are essentially new laboratories for the understanding of atmospheric response to thermal forcing, which is what all of, a lot of meteorology and climate studies is about. So it's fair to say that the field of the study of exoplanetary atmosphere is observationally driven to this day, and it probably stay that way for a while. And so I'm not going to try to attempt to tell you exhaustively all that has been done. This has been going very fast in the last few years. I'll just remind you of some of the basics that have happened. In 2000, this is not actually a result from 2000, but basically in 2000, Dave Charbonneau and his collaborators and actually another group have detected the first transit of hot Jupiter. which confirm what we all expected, but still confirm that these are indeed giant, gaseous giant planets from the measurement of the radius when you combine with the radial velocity survey that you have. And that was around 2000, and this is what motivated actually these early papers that I showed you in the previous slide, which is like, oh, now we have radius, mass, surface gravity, we have an idea of the temperature in the atmosphere. These were the first few elements you need to worry about to think of what's going on in this atmosphere. So this is the beginning of this field from the point of view of modeling. And the real breakthrough in the last few years has been the Spitzer Space Telescope, which was not at all designed to do any of this. And it could be argued that this might be the biggest legacy of the entire Spitzer mission. I mean, I'm not into politics, but some people might argue that way. Certainly the Spitzer team is very excited. They should be. Probably in the last year or year and a half, there were at least a dozen papers in Nature and Science from Spitzer measurements. So it's a big deal. And I'm just reminding you of one such measurement here. This is an eclipse in infrared. We have a hot Jupiter, permanent day side, permanent night side, with some level of heat redistribution. If the day side remains, actually at this level it's not very important, but some of the measurement we would like to do is actually measure to what extent how hot the day side is, which is a measure of how inefficient or efficient redistribution of heat has been in these atmospheres. And so you can look at these transiting systems and measure the infrared flux from the star plus the planet. When the planet goes behind the star, you have a decrement, secondary eclipse. The decrement, this is a direct measure of the amount of light emitted by the day side of the planet. And so that was a big surprise, and a lot more has been done since the first secondary eclipse measurements. I'm just reminding you here, and I'm not trying to be exhaustive, there will be a lot of people to actually credit for all this work, and I'm omitting many of them. Just know that there is a substantial amount of work that has been done here. But the bottom line is that we now have such infrared secondary eclipses, which are these brightness temperature measurements for the day side of several of these hot Jupiters for several planets. In some cases, we have repeated eclipse measurements, which might indicate there is some level of variability in the emission from the day side. Multi-wavelength eclipses, which allows you to get basically spectral energy distribution, broadband spectral energy distributions. Phase curves for a few planets. I'll show you one example in the next slide. People have done great transmission spectroscopy, basically using the fact that so now in transit, when the planet is in front of its star, you get actually absorption features from the limb of the atmospheres, and from that you can actually constrain the atmospheric composition. There is claim detection of water and methane, et cetera, et cetera. There is also there's also infrared spectra from Spitzer that have been measured, claims of evidence for stratospheres, which are region of atmosphere that are very strongly stabilized, or let's say inversion temperatures, claims for inversion temperatures in the atmosphere of some of these planets. And there is also work in the optical about the albedo of these planets from a very precise optical photometry that suggests that these planets have very low albedos from the lack of reflection, basically, of the stellar light. So there's a lot of stuff that has been going on, and this is, I think almost all of this is within the last 2 or 3 years, basically. Let's say 3 years. Let me show you one of the most recent results. It's not quite the most recent measurement, but I think it illustrates well some of the things we have learned about these planets observationally. This is actually half an orbit, 8 micron Spitzer infrared phase curve of the brightest transiting hot Jupiter. I won't give you the name. I don't think that's very important. Here you see when the actually planet goes in front of the star. So that's a transit in infrared. And here you see when the planet is eclipsed by the star. So this is one of the secondary eclipse measurements. But on top of that, if you zoom in here, you continuously stare for half an orbit at the system, you see actually a modulation in the amount of infrared light. And this is consistent with seeing actually more light from the day side than the night side. But even better, the peak, well, I mean, this is model fitting, but there is evidence that the peak emission is actually precedes the secondary eclipse, while if there was a perfect day side, night side asymmetry, you would expect the peak to be exactly at the time of secondary eclipse. So there is evidence for a shift here in the hottest region in the atmospheres, and there might be evidence here for actually a feature You see this bump here, which has not been commented much about, but there might be evidence for features in these phase curves. So this is the level of data that is being acquired right now on these hot Jupiters, and they are really getting at this problem of how efficiently do you transfer heat from the day side to the night side of these atmospheres. One very interesting thing is that if there was no heat redistribution, you would expect the day flux and the night flux to be different by factor several at least. So a much bigger variation than this. This is actually a small variation compared to what you would expect if there was no heat redistribution. So we know right away from this that because the flux variation is at the order of 50%, that there is actually efficient redistribution in the atmospheric layers probed at 8 micron in this planet. And we know that the atmosphere is not in radiative equilibrium. Radiative equilibrium would be this hot, very hot day side, very cold night side, which is not the case. And basically, we know that to understand what's going on here, we need to actually account for atmospheric circulations. And that's one of the key basic motivations for the work I'll show you. And so the question, the general question sort of asked and considered in this, in this talk is, can we understand these different regimes, you know, atmospheres of solar system planets, whether terrestrial or giant, are being externally forced, thermally forced by the sun in some ways that depend on their orbits, their spin rate, and various other things, and they respond to this forcing in the way we see. And these are similarly giant planets that are forced in very different ways. The atmospheres are very hot, they spin very slowly, and then they have this hemispheric forcing, day side, night side. Can we understand the response of these atmospheres to these different regimes, different forcings, conditions? That's a basic question. And can we help interpret the data, understand what's going on in these atmospheres? So one, I'm wondering whether, I cannot see the time actually. Okay, yeah. So one of the points I wanted to make here, which seems actually, well, may seem trivial to some, but I don't think it's necessarily trivial. Well, when you consider it, it sounds trivial, but actually it's an important point. What's the nature of the forcing? What I'm showing you here is the Earth, annual mean radiative energy budget. So you see latitude here, and then this is radiation flux. Blue is coming in. This is solar radiation. Red is coming out, and you can measure that, you know, on the Earth. And so obviously the equator receives more, in a nearly average sense, the equator receives more actually irradiation than the poles. This is well known. But the one thing I want to emphasize on this plot is that from the point of view of fluid at the equator or fluid at the pole, what is important is the net forcing. And the net forcing is the difference between what comes in, the blue minus the red. So you have an energy surplus here, meaning you're heating the atmospheric flow here at the equator because it receives more than it actually emits. And then here, you actually emit more than you receive. This is actually the atmospheric heat engine. And the key thing to realize is that this red curve accounts already for the advection of heat, for the fact that the flow has already adjusted and is advected heat and transported heat in some way. So the point is that the net forcing of the atmospheric flow depends non-linearly on the advection of heat itself. This is the point that's made here. And basically, if you want to understand what's going on in a planetary atmosphere, externally forced planetary atmosphere, that's very different than a star or a brown dwarf. You have to do radiation hydrodynamics, which is something that very few people do, I think, even in astrophysics, actually. But it's fundamentally a radiation hydrodynamics problem. That means it's difficult. You have to solve the hydrodynamics well, and you have to solve the radiation coupled together. And nobody has done that for any extrasolar planet at the moment, I should say, actually. So this is what's going to come up in the next few years. So the point here is that, you know, when we do stellar structure model or brown dwarf models, they are symmetrically forced atmospheres. If you do a model of the atmosphere of brown dwarfs of stars, stellar models, you know, it's spherically, to first approximation, you basically spherically symmetric forcing from inside, but it doesn't matter. Spherically symmetric, you do a 1D model, you're fine. Similarly for white dwarf. When you're dealing with a planet, in general, you actually, you do not have, you basically force asymmetrically the atmosphere, the flow, the fluid, advects the heat, and then you irradiate, suddenly it becomes a radiation hydrodynamics problem. And that makes it much more complicated than what we have been doing for a long time in astrophysics, basically. So this is a distinction between stellar atmosphere, stellar astrophysics, if you will, and planetary atmospheric science. One of the key distinctions.
Well, stellar astrophysics is also going in a different direction, because when you work with X-ray and you hit a star.
That's right. So there are actually very interesting cases in this, in binaries where actually this is probably likely to play a big role. Yeah, but in general, in astrophysics, we like to do one-dimensional models, and here you can't. Well, you might learn something from these models, but the problem is fundamentally a radiation hydrodynamics problem. All right. So then the attitude could be, and this is an attitude I've met several times already talking to people, is that this is hopeless. Because you look at this, actually, I guess it's not very bright. I don't see if you can see, but this is one of the most advanced climate model that has been run for the Earth. There's a lot of interesting going on here. In fact, it's so high resolution, so this is going to be useful for later. T341 is actually a notation for spectral models. It's a resolution measure. It says this is basically equivalent to 1,000 grid points to 500. 1,000 in longitude, 500 in latitude. 37 kilometer resolution. It's a huge simulation that went on the Earth simulator. I'm just showing you 1 month, one specific visualization. But what's going on in this is that you have oceans, you have vegetation models, you have different types of leaves for the vegetation that grow and decay and all this. This is the climate business, okay? It's just mind-boggling. So can we do anything about this distant world? Yes. This is a really this is a big deal simulation. And then you get precipitation, water. So I don't know if you can see these red cycles here, especially on South America. This is every day. It's basically the rainfall, actually. You get tsunamis here. So high resolution that you get weather features in a climate model, meaning like small time scales, small length scales, events. But the one thing I want you to notice is this like tongues of clouds, which are essentially tracers of what the flow is doing, the flow dynamics. And the point I'm going to make now is that this is a 2007, I think, maybe 2006 model. Before these models, trying to address the global warming problem to some extent. That's one of the big motivations. Before these models became so complex and so detailed, they were simpler. And in fact, the backbone of this type of models is a solver of the hydrodynamics equation for a stratified atmosphere on a rotating sphere. And they are known in meteorology and climate as the primitive equations of meteorology. And basically, people have developed very efficient solver for this. And they can be translated to the basically exoplanet atmosphere problem quite effectively. So the backbone is a solver for the hydrodynamics on which you actually add all this extra physics, like clouds, radiation, etc. So look at this. Again, I want to emphasize this like tongues and this typical motion. I don't know if everybody can see them, but basically there's tongues like this going around. Now what I'm going to show you is the model I've been running. This is an Earthlike model. So I take a meteorology solver, solver of primitive equations. And what I do is actually a simple test. People have even designed tests, to check the accuracy of this dynamic solver. What I've been solving here is a very simple Earth mean climatology model, where basically you just say, and this is showing you actually temperature and velocity map at the surface level. It is low resolution, only 15 level, and then this is 120 to 64 equivalent grid point. This is actually spectral. It's not grid point, but the equivalent resolution. And what you do is that you say, I'm shine on average, basically what I showed you before. On average, I shine more, I heat up more my gas here, and then actually, I basically make the flow relax to a hotter temperature here than here in a linear fashion. This is a standard simple test for the dynamics of this flow. And surely enough, what you get from this temperature gradient, equator to pole, you get the development in this multi-layer atmosphere of baroclinic instabilities. You get these tongues. They go in the right direction. There's a right number of them, between 5 and 8 are observed on the Earth. This is by climate standard, it's a crappy simulation. It's 1975 model, essentially, that I'm running in 2008. But the point is that it does capture key features. I would say more than qualitative. It's a question of how quantitative you want to be, but it captures key features of what's going on in the Earth's atmosphere. We can use this simple model and cast them into the exoplanetary atmosphere context and try basically to understand how the flow behaves under different situations, and if we need to, add extra physics. That's basically the idea behind the talk. Yeah.
How many things you need to resolve atmosphere in height?
So this is actually a troposphere plus stratosphere, but the stratosphere is not well described. There's a number of complexities with the stratosphere. But this is basically, actually, there's basically maybe 10 levels in the troposphere and 5 levels in the stratosphere, to give you an idea. Yeah. And the stratosphere is poorly done in this model. It basically, baroclinic instability is a tropospheric feature. So this is what essentially is captured in this model.
But your stratosphere doesn't have any weather, right?
Doesn't have any weather?
Yeah, normally stratosphere doesn't have any weather.
Well, what people call weather, weather, theoretical point of view, weather can be small time scale, small length scale feature. You want to predict the weather, specific vortices. But also what people call weather with reference to storm tracks is the baroclinic instability. Mid-latitude weather. Why do we get storms while there's, the behavior is quite different at the equator? It's because of the baroclinic instability. It's because of these storms. They develop into vortices. And these are cyclones, anticyclones that we know at mid-latitude. This is what people call weather. So that is captured here. What's going on in the stratosphere is not baroclinic instability, is different, and you can do better models to try to capture it. This specific model doesn't do that, but I could run more and modify the models. All I'm pointing to is that with a pretty simple model by climate standards or meteor standards, you can do a reasonable job at getting some key properties of how the Earth's atmosphere behaves. This is just a linear relaxation. So basically, you have an energy equation, which normally you would calculate radiative flux down, up, and this is your heating term or cooling term for this gas parcel. Instead of doing that, you say, oh, I'm going to have a T minus T equilibrium over a radiative timescale. Linear relaxation to a prescribed profile. This is known as Newtonian relaxation in the geophysical literature. So, yeah. And this is what has been done so far for all the hot Jupiter work, basically, actually, this Newtonian relaxation. Now, okay, so now I don't want to give you the impression, which would also be wrong, that, oh, you have this solver, so you just put the parameters, run the thing, and that's it. You have your solution. Because there are a number of complexities. And I picked this abstract from Isaac Held is actually a godfather, sort of one of the big shot for atmospheric dynamics. And he's written this paper. I'm just borrowing the title here to emphasize something that we're not necessarily familiar with in astrophysics, but people doing climate and meteor are, which is the fact that you can simulate something doesn't mean you understand it. These climate models that I showed you is so complex that you can run it, it reproduces yours, but how do you decide that you understand what's going on? Because you have so many variables, so many things, that it's actually difficult to understand. To some extent, if you have a perfect simulation, you reproduce the universe, and you have not learned anything, except that you can reproduce the universe. So there's a key here, which is understanding. And we're going to have to do that as well for these extrasolar planets, atmosphere, which is we can run these models, we will learn something, but it has to be based on basic understanding. And there is understanding that has been developed over the last 50 years or more in geophysical fluid dynamics and climate and planetary sciences for other planets than just the Earth in solar system planets, that we're going to have to borrow principles from to understand what's going on under these different forcing conditions, basically. So it's a mix between having this very efficient solver and actually really understanding what the response, characterize the response in terms of the fundamental understanding that has been developed in the literature before, which is not a literature we are used to, I think, most astronomers are not used to this literature. I personally have been looking at this for a few years now, and it's a vast amount of work. So you have to filter a number of things. But the amount of knowledge is great, and we can use that for exoplanetary atmospheres. So one, and that goes to the question. That goes somewhat to the question that was asked. One of these understanding or knowledge that has been developed in atmospheric science, GFD is for geophysical fluid dynamics, atmospheric science, specifically focusing on the fluid behavior as opposed to clouds or chemistry, blah, 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 is that there is two big regimes of atmospheric behavior, flow behavior. One is barotropic, and the other is baroclinic. And the meaning here is that you can have a flow regime that is barotropic if you get your thermodynamic surfaces to be well aligned. And the equivalent of this is to say you're dealing with an atmosphere that is very well stratified. In the language of stellar physics, very radiative. And then people say it tends to behave barotropically. Then the other regime, which is the regime I showed you in this simulation, this simple simulation of the Earth for the troposphere, is that you get misaligned pressure, let's say pressure and temperature isocontours, and you're able to tap into this misalignment, the potential gravitational energy, develop an instability, which is a key instability, fluid instability that is driving turbulence in the troposphere of the Earth. This is this baroclinic instability I showed you. And how much you are in this regime or this regime depends on how well stratified, how strongly stratified, how radiative your atmosphere is. And in the Earth, for example, I already made that point, that the troposphere is baroclinic. I showed you actually a simulation of this. And then the stratosphere is actually barotropic. And in this regime, I'll just drop that. Actually, the ozone hole that we have all heard about is actually a manifestation of a barotropic flow. It's basically the ozone hole is a manifestation of the winter stratospheric vortex, which is a dynamic feature. And there is specific chemistry going on in this dynamic feature, basically. And I'll show you vortices in exoplanet atmospheres. This is a generic feature of, polar vortices tend to be a generic feature of barotropic flows. So we are very early, we are very early in our modeling. That's one of the things you should take out of this, is that we're very early in our modeling efforts in trying to understand what's going on in these atmospheres. And so you should take everything with a grain of salt. But I think there is a well-defined path for us. And this is what I'm going to try to lay out this path for you. Rather than tell you, oh, this is what's going on, here are the results, because I don't believe what I'm going to show you are the final results anyway. What I'm going to try to defend is that there is a well-defined path for us to get to be able to say, oh, yeah, maybe we know what's going on in these atmospheres. There is some work that has been done that I will not mention so much further along in the talk, but I think I should mention it that there is some extra work by Langton and Laughlin and Dobbs Dixon, who is here. I didn't see Jan. And Lynn, and this is additional work that I won't actually discuss so much, but just know that it's there. So what I'm going to discuss is two specific examples, some of the work that Adam Schumann has been doing and some of the work we have been doing, and I'll show you some of the latest results I have from running this three-dimensional atmospheric model for conditions appropriate to hot Jupiters, basically. So what we try to understand, in a nutshell, is the flow of momentum and energy in this atmosphere, and mass. But what's difficult to capture is flow momentum and energy in these atmospheres. Different forcing schemes have been employed. The issue of forcing itself is difficult because the forcing depends on the flow, as I showed you for the Earth. So exactly how you set up your forcing has an impact on the result of your simulation. So that's a tricky nonlinear thing you have to account for. And specifically, the nonlinear character of the forcing has not been accounted for in any of the simulations that have been run so far, and certainly not in the simulation I'll show you here. What we have done, so I'll basically describe the published work and some preliminary results from work I'm doing currently, is that we believe that the external irradiation from the star has a tendency to make this atmosphere of hot Jupiters very strongly stratified. Plus, they are hot. They are slowly spinning. If you put everything together using the knowledge from geophysical fluid dynamics, that favors a barotropic regime. It looks like it's not obvious to actually drive bioclinic instabilities, like I've shown you in the simulation of the Earth. It looks like we may be more in a barotropic regime. And that is a qualitative statement. But based on that, and assuming indeed we're dealing with a barotropic regime, then you can show that in a barotropic, again, because you have your thermodynamic contours that are well aligned, not misaligned, you can actually get a reasonable realization of the flow in simply using a vertically integrated version of the primitive equation of meteorology. So it's just a one-layer model, and the one layer is because you don't need these slanted surfaces to get the baroclinic instability. Therefore, you can do an okay job with just a one-layer model. And so that's an assumption of our modeling. So we use this like what's known as the equivalent barotropic formulation of the primitive equation of meteorology, which is related but different from shallow water. This is something, it's a technical point anyway. And because this, what we have shown, what we have published so far are adiabatic simulations, we actually don't explicitly force the flow radiatively. What we do is that we seed turbulence in the flow and ask, in this context of a turbulent medium, given this general condition of spin, typical scale height of the atmosphere, rotation rate, and surface gravity, radius of the planet, what sort of two-dimensional barotropic turbulent flow do you get realized on this planet? That's basically the work we have done. And also, we deform the layer to account for the fact that there might be a hotter day side and a cooler night side. So that accounts in a mechanical way for the fact that the heat transport is not 100% efficient, as seen in the phase curve I showed you.
I understand. So you do have a hot side and a cold side. Why is it barotropic?
I mean, these are two normal, orthogonal statements. You know, you can have a day side and night side and be mostly in a barotropic.
But the pressure gradient do not have to be parallel to the.
Yeah, so it's a qualitative statement. The point is that it's every atmosphere is baroclinic. You know, it's obviously you never get exactly, except maybe in white dwarfs or whatever, very special conditions you could imagine where actually you get a baroclinic is a most general situation that's realized. But now you have to borrow on the knowledge that has been developed in GFD that says if you have a rather well-stratified atmosphere, the flow will behave rather barotropically, and you will capture key feature not accounting for baroclinic instability. And this is what we're counting on here. And this high Brent-Weisler frequency, positive. No, so that's another business. No. Okay, so the statement has to do with what's known, and I'll get to that in a few slides, what's known as the Rossby deformation radius, which is a typical length scale of the most violently unstable baroclinic modes. And if that is very, very small compared to the planetary scales, or large compared to the planetary scales, which is the case here, then you don't expect baroclinic instabilities to be violently driving your flow. This is a quantitative statement I can make for you. It's related to slow rotation, the level of stratification, the rotation rate. It's all together. No, that's a dynamical statement I'm doing here.
The Rossby number is about, the Rossby.
That depends on the wind speed that we don't know.
Right, but it's about planetary radius, right? In this case.
Yeah, it might not be very much smaller than unity. Yes, it might be over unity. Yes, I think that's a reasonable yes. But this is not Rossby number. I said Rossby deformation radius. That's a different quantity. Yes. Well, this gets into rather technical points, so maybe we can leave that for yeah.
What kind of Reynolds number for these big simulations?
Well, it depends how you want to define your Reynolds number. You mean the numerical Reynolds number?
Well, that's appropriate for the simulation.
Well, that's a multifaceted question. you can calculate the Reynolds number using this typical, argument. This is a numerical Reynolds number anyway. Are you asking what the physics of the problem? Because the physics is essentially infinite Reynolds number. And I think that's what maybe you're asking, which is that to first approximation, microscopic diffusion process, at the 1 bar level and also in the troposphere of the Earth and even the stratosphere, you don't worry about microscopic diffusion process. So it's a infinite Reynolds number problem with a small dissipative scale for what's going on small scale. Yeah, is that what you were asking?
Yes.
Yeah, so it's a high Reynolds number, like most astrophysical flows actually, yes. So the question that was asked in this simulation, given a prescribed amount of deformation of the bottom layers, which is a measure of how well you redistribute heat. Remember, these are adiabatic simulations, so you actually don't solve an energy equation, purely dynamics. And given a prescribed wind speed, which is seated in this initial turbulence, what of flow are realized? And this is a very different question than some of the questions that have been addressed by other people who have looked at this problem. So the answers you get are also somewhat different. Yeah.
If the planet's not rotating, the velocity deformation radius is infinite, is that right?
Yes.
So you could say that all non-rotating planets are in the barotropism.
Well, I don't think that's a well-defined. You're looking at an extreme here. I don't think that's well-defined. But I'm not sure that's well-defined. From what I said, it's what it sounds. I'm just not sure that's true, actually. But anyway, geophysical fluid dynamics deals with stratified rotating flows. And so you don't care about the non-rotating one. What you're asking is whether you're more in a fast rotating, slow rotating, barotropic, baroclinic is actually what matters. Well, what I mean by this is actually I added adiabatic because we don't solve an energy equation. So we don't force the flow. We don't have this radiative forcing in any way. Yeah, okay. So adiabatic, and then turbulent seated, you actually put small scale turbulence on a sphere in a layer and you let it evolve by itself. And it turns out that two-dimensional turbulence had a tendency to, energy goes to large scales. So you realize this large scale flow. This is something that's well understood from geophysical fluid dynamics. And so you ask, what is a flow realized on these planets, basically? Yeah. So in fact, these are high enough resolution that to a very good approximation, you conserve energy, kinetic energy in the flow. That's because that's because the energy goes to large scales where there is no actually formal dissipation in the simulation. So it's basically you seed the wind speed or the kinetic energy from the start, and that is very little change over time. So here is, I guess, a visual representation of what has come out of these simulations. And again, assuming we're dealing with a turbulent barotropic flow and not solving for the actual energetics of the problem, this is the sort of flow we might expect. And what I'm showing you here is a potential vorticity, which is actually an active flow tracer. So you can show, especially in one-layer models, that it's the Lagrangian derivative of potential vorticity is conserved. So basically, you take a snapshot of potential vorticity map, it tells you what the flow is doing at that point in time. So basically, what you can sort of visualize from these colors is that you get this broad wind, you get actually what is known as Rossby waves, they break, and you get these very strong cyclonic polar vortices. And then this feature moved around, you get a cold, because they are cyclonic vortices, you get actually cold spots associated with this vortices, and this is the same resolution as I showed you in these big climate studies, same horizontal resolution, but they have 70 layers and they have all this extra physics. This is pure dynamics. So it's actually much simpler to run than what they have done. Anti-stellar point and anti-stellar point. So the star is here and then on the backside, yeah. And the point is that what we found is that this generic flow pattern is not too strongly modified if we change the amount of bending of the bottom layer, which is a measure of how much heat is redistributed. Remember, this is adiabatic. We don't solve for an energy equation, so we actually parameterize the amount of deformation of the atmospheric layer model from the fact that you would have hotter region that would actually, basically support at somewhat higher zero potential, if you will, this layer compared to from the day side to the night side. And what's important is that from a parameter space survey, this flow seems to be rather generic. No matter how big I shouldn't say no matter how big, but basically it's not strongly sensitive to the amount of bending.
So for this to recover, then that's an all phase shift in the hot spot.
No, so here again, this is actually we don't solve for thermodynamics of the flow. So it would be very daring of us. We could use the mass equation to but that would be I'll show you actually some attempts to do this. But I think this has to be taken with a grain of salt. So I'll show you in a moment what we get actually with respect to the phase curves. So the basic point is that we get a dynamic atmosphere, turbulent. That's an assumption of this model, I should say. Turbulent atmosphere with large-scale features, broad equatorial wind that goes actually in the opposite direction of the spin rotation of the planet, and then these big vortices. No? Initially.
So the feature around the North Pole is somewhere you can expect it, but why there is no same feature around the South Pole, or why it's sort of shifting?
Oh, well, yeah. So because there is bending, we believe that, there's a few things. Is that this jet itself is so powerful, and these large-scale wiggles, which can be understood as a large Rossby wave, if you will, that itself has to do with the fact that you have, you have a bending of these layers from the bottom, day side, night side. This basically knocks off the polar vortex of the pole. That's our interpretation of why. And in this specific case, it's aligned. But in other simulations, this is turbulent, so you have to try with many different initial conditions. We do find it somewhat offset in general. And then advected by the flow. So one of the, all right, I'll come to the, if you will, relation to observation in a moment. Even so, I think it's tenuous at the moment.
You start out with potential vorticity,
Yes.
some distribution.
Yes.
Be concentrated on the anti-solar.
No. Uniformly distributed, small scale, and then you let the turbulence do the cascade.
And how does it know about the star?
Oh, it doesn't know about the star except that you actually you basically bend the bottom layer. And the idea here is that you have an extra layer below, if you will, which is hotter, and therefore you have a flow which is not at constant geopotential, but actually is bent. So we have a mechanical prescription for the heating, but that's all we have. Well, we don't solve a temperature equation. It's mass conservation and momentum, and then we bend the bottom layer, which is a proxy for a flow in a layer on top of a hot day side and cold night side. Is that? Yes. Does that answer? Yeah. I'll show you actually three-dimensional models that do solve the energetics. So I want to make sure I get to that. But what's important is that, again, do we understand what comes out of this simulation? Because we were talking about dark matter simulation. It's like, how do you trust what comes out of your computer? It's very easy to get a lot of numbers, but there is actually some understanding, again, in geophysical fluid dynamics, that two-dimensional turbulence behaves in a way that is determined to a large extent by this Rhine's length. And don't ask me the definition because I don't know it by heart. I can give you the Rossby deformation radius because that one I know. But it's largely determined by the Rhine's length and Rossby deformation radius. So the Rossby deformation radius I already mentioned determines the scale for the fastest growing bioclinic waves or eddies or whatever. But it also is a causality scale for structures in the flow. And the thing is that this is how it comes about. Square root of g, this is the Rossby deformation radius. This is actually the speed of horizontal gravity waves. And these are the fastest mode you have in actually a hydrostatically balanced atmosphere. So they are the fast mode. They are the equivalent of sound waves in a hydrostatically balanced atmosphere, horizontal sound waves, if you will, or they're related to horizontal sound wave. And this is rotation. And if you go, actually, I think I got that right, beyond the Rossby deformation radius, it's not possible for the flow to basically be causally connected. Rotation acts in such a way that even your fast gravity modes are not able to communicate from one side to the other over a rotation period. And so effectively, it is known to act as a causality scale for features, for in particular vortices, but for atmospheric turbulent features. And so that is of order the planetary radius. So you get very large scales, like this big polar vortex. Jupiter doesn't have a big polar vortex because the Rossby deformation radius is much smaller, actually. You get plenty of smaller vortices. That's one understanding that we have about what's going on. And the Rhine's length has to do with the anisotropy of turbulence. You know, you're free to grow, two-dimensional turbulence grow to large scales. You're free to grow in longitude, but in latitude, because you tend to conserve angular momentum or equivalently potential vorticity, you are constrained by Coriolis force if you move up. So effectively, the gradient of the Coriolis force impacts the turbulence and makes it anisotropic, just from the geometry of a spherical rotating object. And as a result, you tend to grow actually these jets or winds, like I showed you here. You know, these winds. You cannot grow scale very easily in latitude, but except that the typical limiting scale that you can grow from two-dimensional turbulence in latitude is determined by this Rhine's length. And effectively, it determines the width of the bending of the jets you have, basically these winds one direction, the other, etc. On Jupiter, again, small Rhine's lengths, you get actually many alternating jets as you go from the equator to the pole. On these planets, it's again a very large number because of the slow rotation. And so you get a broad equatorial wind. This is again purely dynamical classification of the flow on these planets, basically. So the last thing, so wide equatorial jet and large polar vortices are basically understood with these two fundamental scales in geophysical fluid dynamics. Now, clearly, these are far from being satisfactory simulations, but this is what we have done. Assuming you have a turbulent barotropic flow, you might expect this sort of flow realized on these planets. One of the things we have emphasized in relation to observations is that because these are big features, especially you could think of these polar vortices that are actually cold, they are translating around. They might create, because the flow is turbulent, they might create actually variability in the observational properties of the planets. You know, in the same way cyclones and anticyclones are cold, when low pressure, high pressure, good weather, bad weather is basically pressure or temperature related. These guys are cold, and if they translate in front of you while you're taking a Spitzer infrared secondary eclipse, and the next time it's not there, there might be some amount of variability. That's one of the possible consequences of this flow that we have emphasized. And let me show you to answer Norm's question. And I don't want, well, a few phase curves with a prescribed amount of deformation, 5% of the layer thickness at the bottom, different wind speed, meaning initial value of the kinetic energy in the turbulence. We see it in the simulation. If you go to high values, you actually get a lot of deformation and features of this phase curve. If you just integrate the thermal emission, this is an extremely simple model for what you might be able to see from this planet. You get features and a lack of repeatability of the eclipses. At high wind speed, at low wind speeds, you don't see actually the features themselves deforming the phase curve much, basically.
What's the velocity of Jupiter?
Oh yeah, the highest on the solar system is 400 meters per second. Jupiter is 50 meters per second. And then the three other planets are 400. I mean, this is RMS wind speed. Yeah. All right. So this is, I mean, I think sort of the sense of the question I'm getting and trying to understand what's going on here is that, well, part of the criticism that has been pointed toward this model is that you don't, it's one-dimensional model. You don't solve for the relative transfer or the flow energetic. So it's hard to appreciate how is it that this will be realized if you put extra physics? How does that combine with actually the actual forcing of the atmosphere, which is not included here? Here, the forcing is just from this small-scale initial turbulence. So obviously, the future in the field is going to be to move to these solvers of three-dimensional meteorological equations, actually put the forcing in and look at what you get and try to understand, again, the response that you get. And so efficient solvers have been developed over decades in meteorology and for climate studies. There are these backbones that I mentioned, and one example is this model that I used to show you this Earth validation. I basically acquired this model, installed it, ran it, understood it to a fair extent, and then checked that it runs properly and does reproduce the Earth when I expect it to reproduce the Earth, which is what I showed you, is basically model validation. And one thing that's going to be important in the future of this field is because it's tricky to solve these equations well, making sure you actually conserve, for instance, horizontal resolution is an issue, and making sure actually you conserve energy and momentum through the various layers. People have designed very, very advanced schemes to actually do that properly, to machine precision, if you will. And so we will need to do intercomparisons. People using different codes, getting possibly different results. Because this model have been, these solvers have been emphasizing mostly the Earth. They've been designed to treat let's say, the baroclinic Earth model well, for instance. And we are going to different regimes. So how are we sure that we get consistent answers from different codes? And so one example of these sort of things we want to do is to take this spectral code, which is the code I'm running currently. Take similar setup to a grid code. And what I'm showing you here is actually Adam Schauman's early work, the very early work that he has done on this. This is longitude, latitude, and for similar setup, you would expect to get similar results. And certainly there is qualitatively something that's similar here, but there are also significant differences, and we want to understand this to some extent. I should mention that, so the basic flow that Adam gets in the simulation, and I think the latest one as well, is actually the super rotation, meaning the equatorial wind is going actually in the same direction as the planets, which is the opposite of what I showed you in these barotropic results before. And then you get this advection of the hotspot by some degrees. And you get some of this here, but actually here the winds are subsonic, and some of his winds are supersonic, which is a regime that has never been seen. It's not in the solar system, all the winds are subsonic. So it's a new regime. We want to do code comparison. The solvers for the vertical and the solver for the horizontal are very different. This is spectral grid. So you want to actually do this intercomparison and see whether you get consistent result. That would convince you and the community that you know what you're doing. And so this is what I'm doing currently. I have defined actually now, and I've run what I call this hot Jupiter benchmark model. And few people have seen this. I don't know if you can see it because actually it's not very bright. But this is actually a benchmark calculation. I will publish it and say, listen, this is the parameters, very few of them, as few as possible. This is the flow I get with my spectral solver. This is my solver. Show that you can reproduce the same flow. And we should have consistent results. If not, there is a problem, and we need to figure out what's going on. And so what I'm showing you here is this 0.4 bar level of a multi-layer model. The range of temperature is not very important. This is a substellar point. This is the night side here, antistellar point. You do get some advection. You do get a super rotating equatorial wind, like Adam has been getting. But you also get these polar vortices. I don't know if you can see this here. Very large polar vortices. The winds are subsonic. So clearly there are features that are common to some of these equivalent barotropic flow results I showed you, some results that are common to what Adam Schauman and his collaborators have published, and some that are different. And this, let me actually summarize what's coming out of this benchmark calculation. Subsonic wind, unsteady flow. I cannot tell right now for sure whether this is just wave activity or if it's really turbulent. And for that, I need probably to look at a spectrum. Turbulence is a very specific to prove that you have a turbulent flow, you need to do a number of things. I have not done that yet, but certainly the flow is unsteady. The flow is also very vertically aligned. If I showed you 1 bar level or 0.2 bar level, you would see about the same structure, and specifically the same vortices. They're somewhat tilted, but they're there. So indeed, it's a barotropic flow. I don't see any evidence for baroclinic instability. As I said, there is a super-rotating wind, like some of what the other simulations have produced. And you get a heat-shifted hotspot, which might be consistent with this phase curve. This is what you need, actually, to explain this peak emission a little bit before the secondary eclipse. Opposite, yeah. Yes. Well, it seems like you have to understand what's the process. I mean, getting super rotation is very tricky because by pure angular momentum conservation, if you raise, well, you can show there's a Hyde theorem in geophysical fluid dynamics that you need to not conserve angular momentum to get super rotation. That's purely from the geometry of the planet at the equator. And so for angular momentum not to be conserved, you need either wave activity or turbulence going counter gradients. So it's not tricky. And so, but it might be that process you cannot achieve. Well, it's actually that process you might not be able to achieve easily in one-dimensional. So it's known that it's difficult to get this in one-dimensional modulation. So it looks like you need the multi-layer to get that right. Yeah. I guess I have only 0 minutes or 5 minutes. Okay, I'm gonna have to skip a number of things. So the view I'm defending here is that. The way the field has been is that we had published our results, and then there were other results published, and they look like very different. I think we might see, I hope we might see a convergence of what's going on in these atmospheres in the next few years. And what I've been working on for the moment is defining a simple benchmark calculation we can all test our codes against. And certainly the way to go is multi-layer. I mean, there's no question. This is, again, Newtonian relaxation. You force a flow field to on a specific time scale to a specific profile of temperature. And once we get our act together and hopefully we get consistent results, then we'll be able to move forward to actually try to explain what's going on, what is seen in the phase curve and secondary eclipses, evidence for variability and all this, or lack of variability, etc. So I'm going to finish just with the future of the field. Just give you a preview. I guess we'll get more data. There's phase curves that have been acquired recently or are being acquired, repeated secondary eclipses. There is tentative evidence for variability. One published results, some of the people I'm working on have also actually, including my student, have some evidence for variability in another system. It's not very strong variability, but it might be there. Spectra, probably people will try to acquire better spectra. Essentially, better Spitzer data. But Spitzer cryogenic is going away, and soon that's going to be end of it. I think there will be a phase of code development and checking and optimization and etc. And then what's going to happen in this field is that when JWST flies, it might be able to, with this like 100-fold sensitivity compared to Spitzer, it might be able to actually provide us precision measurements on this like hot Jupiters, atmospheres, atmospheric flows, and we'll be able to actually try to interpret this data with improved models. And so that's what's going to happen, I think, in the next few years. That there is a well-defined track. People have modeled the Earth, and then when data became available for Mars, they started doing what they call general circulation models of Mars, and then they did Venus, and then lately people have been doing some of Jupiter. And you start with the hydrodynamics because that's the part that's most difficult to code as a solver, and then you add radiation, you do radiation hydrodynamics, and you add chemistry, cloud, etc. There's a well-defined track that we can hope to follow for exoplanetary atmospheres, basically. And another point that we can argue about is that I think one thing that's important to realize is that the constraints are rather loose. So we're not trying to get a % precision model fitting to the data. Here we're trying to get qualitative and maybe agreement at the 10% level. And that might be doable even though we know so little about what these atmospheres, even though they're remote atmospheres, we are very indirect probe of what's going on. And then the last slide, I guess, before my conclusion is that, and if you're not convinced by this, I think you might be convinced by this. In the sense that what's going on now is a training ground for what's coming up in 5, 6, or 7 years from now, which is the fact that JWST might be able to basically measure secondary eclipses, phase curves, maybe even spectra of terrestrial planets in the habitable zone or nearby M dwarf. If you do purely and this is a point that was recommended by the Exoplanet Task Force, but was pointed out by Dave Charbonneau and Drake Daming, you just do a signal-to-noise analysis, and you say, given the higher sensitivity, nearby M dwarf, I put an Earth. Oh yes, I can do all these measurements that are barely doable with Spitzer. We believe they will be doable for terrestrial planets with liquid surface conditions around nearby M dwarfs, and they will be tidally locked. And a lot of what the knowledge that will develop for hot Jupiters being tidally locked and how their atmosphere respond, modulo the lack of a hard surface, will carry over to this problem. And I'll stop here with my conclusion. I had a few more things about climate, but I'll skip it. So basically, I tried to make a few qualitative points. And you all know that now, planetary atmospheres, exoplanetary atmospheres are now accessible to us, barely, but they are, and it's going to only get better and better. And so we can tune meteorological and climate tools to actually try to understand what's going on in these atmospheres. And if we do, we have new laboratories to understand the response of atmospheres to forcings. And there's a strong tie, in relation to my last slide, there's a strong tie to this notion of trying to search for life elsewhere. These terrestrial planets around nearby M dwarfs may be habitable, and we may have direct constraints on the surface temperature condition on these planets, and we would want to understand, again, this very unusual forcing condition of the atmosphere and the climate on these planets, whether it allows for life or not. And I'll stop here. Oh, yeah. I just see this one. I just want to mention one thing. It's likely that there will be a UCSB KITP program on exoplanets in 2010. It's not quite finally approved yet, but anybody who is interested in exoplanets should keep that in mind for the early 2010. Yeah.
I guess we have time for only one or two questions.
I couldn't see the effect of rotation here. Presumably, if you have planets further out, the rotation rates are locked at slower rates. Is there I know that Jim Castings and students have been looking at that.
Oh, you're talking about just this? This problem, you mean?
Well, it's just, you showed your results for a particular rotation rate.
Yes.
So
Yeah, you're asking for, yes. So because what I was trying to define is a benchmark calculation that people can compare to. But then the next stage, I think, and it will be very important because we know so little about the details of these atmospheres, will be to survey parameter space and understand how reliable, how deterministic, in a statistical sense, the results are in the simulation. That's actually so I have not done that yet. And I know some people have started, changing the parameters, but we're just starting to do this,
okay.
Yeah.
There are big effects there.
I have tried a little bit if you want to know, and I can change the rotation rate by a factor of 2, and I don't qualitatively change. I don't want you to get the impression this is hopeless. In fact, it is not. You can change many of the global planetary parameters by 10, 20%, and you get a flow that is qualitatively the same. There is quantitative differences, but qualitatively it's the same. So this is where the hope is that there is some determinism in actually this problem. And actually it's known there is some determinism in this problem from geophysical fluid dynamics.
So just here for curiosity, how many planets have you observed by Spitzer so far?
I think secondary eclipses, the count I remember is 6. But there might be 1 or 2 I'm missing. I mean, you can only do the really bright ones. And in fact, what has happened is that people have found brighter ones than the one that were known, and then they turn Spitzer on. So actually, it's partly determined by the efficiency of these ground-based transit surveys to actually be able to find new nearby, meaning bright, or very close to the star planets.